Hello, AP Chemistry, and welcome to Energy. So this is mostly 5.1 and 5.2, where we just talk about an introduction to energy. What is energy? Types of energy? What do we use energy for? All of which should be really, I think it should be really sensible, right? Things that we should mostly know, right? For chemistry, so those of you that are in physics, right, you guys learn about lots of different kinds of energy. In chemistry, mostly we're talking about potential energy. And when we talk about potential energy, we're talking about the energy that has to do with chemical bonds. And not just bonds, but attractions, which we will differentiate when we get to the next unit, actually. Chemical bonds, right, and attractions. That's mostly what we deal with in chemistry. Gases, we do talk about kinetic energy, right? And that goes back to the what? Right. KMT, right? Kinetic molecular theory, when we talk about the movement of my particles, right? And obviously KE applies mostly to gases because gases have huge amounts of kinetic energy, right? As particles that are moving constantly long distances, usually, right? Especially for their size. So when we get to gases, or when we talk about gases, we are often referring to kinetic energy, right? And one of those things that we should know, right, is this equation for kinetic energy, where kinetic energy is equal to 1/2 mv squared. We're also going to talk about a different way to talk about average kinetic energy in a couple of chapters when we get to our gases, right, which is more related to temperature, right? And if we think back to sophomore year, when we defined temperature, right, what was temperature? Right, temperature was the kinetic energy of my particles, right? It was a measure of how much movement, right, the random motions of my particles. And the more kinetic energy my particles have, the higher their overall temperature, right? So kinetic energy is also tied to that. But for particles, right, when we're talking about particles, this is often one of the equations we use. This I wanted to point out because unit analysis is hugely important in chemistry, which means that whether you've ever thought about it or not, right, you already know that joules as a unit can also be expressed as kilograms times meters squared per second squared, right? Wherein joules means kilograms times meters squared over second squared. And that can be really, really useful because in terms of looking at a chemistry problem, if you can see the units and you understand stoichiometry, right, the process of making my units cancel, that's really all you need to know to solve some problems. Anyway, that brings us to our electrostatic kinetic energy equation, which for right now, we're not going to use it very much in this chapter, but in the next chapter, basically that's going to explain almost all of what happens over here, right? Wherein our electrostatic energy equation, right, says that we have a constant, right, Q1, Q2 over R, right? Where Q is charge of particle 1, Q is charge of particle 2. Depending on the kinds of particles, right, we can have whole number charges, partial charges, depends on what we're talking about, right? And this is the distance between them, right, or half the distance between them, which is related to the distance between them. This is really, really important. This is also known as Coulomb's law, or Coulomb's law is derived from this, where basically as charges increase, right, we get more attraction, right? As our radius increases, right, if our radius increases, what happens to this? It goes down, right? So the further apart my particles are, this is going to go down, right? Anyway, very, very important. Make sure you jot this down. We're going to refer back to this in the next unit. Okay, point of view and the first law. First law states, right, energy is conserved, which means that we can trace it from one place to another, which means our point of view is really, really important. Last year we kind of glazed over the whole point of view, right? We just sort of generally talked about exothermic and endothermic. This year it becomes hugely important that we can define our point of view so we can trace the energy, okay? So for starters, let's say we have a hot plate and on it a beaker full of water, okay? So we know that when we turn this hot plate to on, right? So let's say we turn it on, what's happening? Right, we have heat being transferred from here into here, right? We have movement of heat from the hot plate into the water, right? Courtesy of the flow of electrons, right, coming out of our little plug, right? And that flow of electrons heats this up, right? Flows through wires, basically, right? And those wires release a lot of heat because they have a lot of resistance. That heat then ends up in my water. As this water, so we know that the heat coming out of here, the heat coming out of the hot plate is exactly the heat that gets absorbed or goes into the water, right? And as that water absorbs that heat, right, several things happen, again, which we'll talk more about in the next chapter, right? But as that water absorbs that heat, right, we get more movement of my particles, more kinetic energy, eventually our temperature increases, right? We start talking about braking attractions, things like that, right? But we can track this, right? We know energy coming into my hot plate, energy goes into my water, right? And then energy gets absorbed by my water and eventually turns into kinetic energy and other motions for my molecules, right? Likewise here, this one's a little bit more thoughtful, right? And this is going to be what we play with most of this chapter. Here we have some calcium chloride solid, which we're going to dump into a beaker of water. Is this a chemical reaction? No, right? By standard definitions, no, it's not a chemical reaction. We're not producing something that is decidedly new, okay? We're just dissolving my calcium chloride. Okay. Now, it turns out that when we add this calcium chloride into here, right, what do we know is going to happen? Right, we're going to form some calcium ions and we're going to form chloride ions. And we know that what's going to happen between those calcium ions and chloride ions and the water? Right, the water's going to come and surround the calcium, surround my chlorides, right, in a direction-oriented way. Okay, now we also know that when we do this, right, the temperature of my water increases. Okay, when we add my calcium chloride and it dissolves, right, the temperature of my water goes up. What does that mean? Right, going back to the fact that energy is conserved, if the temperature of my water goes up, right, that means my water absorbed energy. That is so sloppy, I'm sorry. Absorbed energy. If my water absorbed energy, what does that mean? Right. Something gave away energy, right? If energy went into the water, it had to come out of something else. Turns out it comes out of this process, right? It turns out that a lot of our compounds, sorry, this should say solid. When we take calcium chloride and we dissociate it into ions, turns out this is an exothermic process. This process releases heat, and that heat gets absorbed by the water, right? There are also salts that when we dissolve them, the temperature of the water would go down, which would mean that, ding, 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 opposite process, right? The salt is absorbing energy from the water, right, as the dissolving occurs. And we'll talk more about that also, actually shortly. Okay. A couple of energy diagrams to make sure you understand, right? If we have an initial energy, right, and then we have a final energy that is lower, right, energy is released from the system, which means that this amount of energy must find itself in the surroundings, right? Likewise here, if we gain this much energy, then the surroundings must have given away, right, or released that much energy, okay? Because we're always looking at it, right, and defining it from a point of view. Okay, here we have another diagram of the same basic thing, right, wherein the energy is released here, which means that if we want to go up this way, right, we would have to put energy in, yeah? So again, if we go this direction, energy is released. If we wanted to go in this direction, energy has to be absorbed, yes? Good. Which is why, right, when we look at a reaction that happens in one direction, it won't necessarily happen in the other direction. Flashing back to the last demo we did in the previous chapter, we took a piece of copper and we added it to some silver nitrate, aqueous, and then we made us some solid silver and some aqueous copper nitrate. Now, this reaction happened all by itself, right? This turned into this and we made some solid silver. Now, bearing that in mind, right, what we should be able to extract from that is that if we then took some solid silver, and intuitively, I'm sure you guys know this without, being able to put words to it, right? This process doesn't happen by itself, yes? Which we must intuitively understand, right? If this mixed together was going to form this, then we wouldn't see any net reaction, yeah? Macroscopically, if this was going to turn back into this, and this was going to turn into this, macroscopically, we wouldn't see anything, okay? Which actually is foreshadowing to when we get to equilibrium. So that means that if we know this occurs in this direction, right, we also know that this backwards one not going to occur under those same conditions, okay? All right. Finally, that brings us to this last figure, right, which goes to the whole concept of state functions, wherein we have heat and work versus just heat, but it doesn't matter because this battery has a defined amount of energy that it will lose. Yes, right? This battery has a defined amount of energy, and however we zap that energy, we still get the same amount of energy out, right? Just sometimes we can be more productive or not. In physics, you do a lot with this whole work component, right? What kind of work can we get out? Work meaning when you're moving something, right? Your book talks a lot about the concept of a piston, right, which literally drives all of our cars, right? The concept of a piston, right, and how we have a gas that is sealed in a piston, and that gas can then expand and contract, right, and work is done, right? And sometimes we actually just want heat to be produced, right, in the form of like a hot plate or a stove, for example. Heat is what we're looking for, right? And then sometimes we get a mixture of both. Like, for example, when you leave something running for a while, you notice that it tends to get warm, right? Going back to physics, right, because sometimes our energy, pretty much all the time, yes, all the time, we lose some to heat courtesy of resistance, yeah? Okay, anyway, this is just a basic introduction to energy concepts, point of view, and things you need to know from there, right? 5.1 and 5.2 gets kind of dense, and a lot of that is actually beyond what we need to know, okay? You just need to be comfortable with energy as a concept, right? Energy as in, it has to be defined from a point of view, right? And the fact that we can track energy from one place to the next place to the next place, okay? Okay, we're going to pause here and we will pick up in the next one. Thank you for listening. Be good, and I'll see you soon. Bye.